All right, today's lesson, starting with polynomial functions and their graphs in section 2. We will learn a little bit about our characteristics. We know about lines, we know about parabolas, but now when we change it and we go to higher degrees, third degree, fourth degree, fifth degree, things start happening with our graphs of these polynomials. So we're going to find out some new characteristics and how we deal with those. So you can see here we want to identify and describe the important features of the graph. And we want to be able to model it with real-world data. So we're going to do a little of each of those. So starting with polynomial functions and their graphs. In the past, we've had what we've called a minimum or maximum point. Now, as we expand and get into larger degree polynomials, we are going to now add to that what we call a local min and a local max. So now take a good look here. A local maximum, when a function rises, then falls over an interval from left to right. So in here, it's rising and then starting to fall. There it's going to have a local maximum. So point A would be considered a local maximum point. Versus, look at point B. When a function falls, which is what it's doing between here and here, but then starts rising again. So now that has to be a local minimum. So we had our parabolas before where we really only had one max or min, but now if our graphs have several things going on in them, we might have some local minimum and maximums, and that's what that's about. So it's still the low point and the high point, but only over a certain little interval. Now, those points of local mins and local max are referred to as turning points, points on the graph that correspond to those minimum and maximum points. There could be more than one minimum point, as I drew on this one, and there could be more than one maximum. It just doesn't curve once or twice. You're going to see some very strange new graphs that you have not seen before. Functions change from increasing to decreasing or from decreasing to increasing at those turning points. So up here again, let's get a little of this off. When we were reading this left to right, this is increasing. It hits point A and it starts to decrease. Continues, continues, it's decreasing, hits point B, and it starts to increase. So you're seeing both situations, from increasing to decreasing and from decreasing to increasing, you will have a turning point. Now, this is key. A polynomial function, so all our polynomial functions, linear, quadratic, cubic, quartic, quintic, all our degrees. A polynomial function of degree n has at most n minus 1 turning points. Notice it says at most. So if I am second degree, it will have at most 1 turning point. If I am a third degree, I will have at most 2 turning points. Fourth degree, 3. Fifth degree, 4. You can see, but it says at most. That doesn't mean you will always have that many. At the most, and it is categorizing it like that. So knowing that, we want to talk about a continuous function. Continuous function, if we just focus on the one first, a continuous function is a graph that goes on. No stops, no breaks, unbroken graph. So we've done several already. We've got our quadratic is a continuous function. We've had our cubed graphs, continuous. There are no holes, no breaks, they keep going. Okay? Both good examples. Versus a discontinuous function, it has breaks or holes in the graph. Now, we've had several of these in our work already, not even new stuff. But if you think about our step graphs, okay, yes, they have holes. Now, sometimes there might be a situation, we haven't seen any, where there definitely would be a hole if we never had that connect and open. You know, I'm just trying to come up with situations that, maybe you can't have anything at that value, but the rest of it looks pretty good. Closed and open, closed and open. So a step function with a specific hole might be the problem. We've had broken line graphs, maybe that go like this, then there was something here, and then it started again over here, because if there was interruption in something and we were graphing it, you would definitely have that hole. So it's discontinuous, has a hole, has a broken point in it. It's a discontinuous function. You are definitely going to see probably a few more like that in this chapter. Okay? So from here, let's go to a polynomial function. Every polynomial function is continuous for all values of x. So the domain is all real numbers. What about the range? So if you have polynomial functions, they will have a range to them, and it sort of depends. We've already done even-powered graphs, and all our even-powered graphs had some kind of upward motion this way, 4th degree, 6th degree. So they were all really above the axis. What about the range? Well, on the range, it'll depend on what your degrees were. Here, if I was graphing this, just plain and simple, the domain, all reals. The range is only going to be non-negative reals, because we do get the 0 and above. If I had a one of our S-curve ones, all reals left and right, all reals up and down. So it is going to depend upon the degree of your polynomial as to what your range or outcome will be. It also depends on what happens at the ends. So when I say at the ends, I'm ending the graph obviously at the end of that, and I'm ending the graph obviously at the end of that. So what's happening at the end, or what I call end behavior here, is different on different polynomial functions. The leading coefficient, we said in our problem, so leading coefficient, if I said y equals 3x to the 4th plus 2x squared plus 1, the leading coefficient here is a 3. If it's in standard form, the highest degree term should be first, and the variable then has a coefficient in front of it, and that coefficient is the coefficient of the term of the greatest degree, referred to as the leading coefficient. So he should be first. The end behavior, as I was talking about, what happens to the function as the domain values get very large or small, it depends on the sign of the leading coefficient and whether the degree of the polynomial is odd or even. So we already have some ideas of what happens when they're even, what happens when they're odd, and we just told you here that that definitely is going to be true. It also depends upon if your function was a positive or negative value on that leading coefficient. That definitely changes it. So I'd graph some too here. I could have graphed them down there just as easily. So the end behavior, and we'll have a graph here that talks about that just a little more detail. What happens to a graph at the end? And it depends on two things, the leading coefficient and whether the polynomial is odd or even degree. So here we go. If we were to graph y equals, or p of x equals, and so get your grapher out, so we do not have to do this by hand. If you were to graph y equals negative 2x to the third minus x squared plus 5x plus 6, and you graph that, you definitely won't be getting just a nice little parabola. Okay? As a quick check on a standard window, I'm getting a motion here. Whoops. Let's bring that a little closer. I'm getting downward motion here, hits a low point, heads back up, not quite as high as the other, hits a high point, and then starts traveling down. So just as a quick graph to make sure you graphed it accurately, something like that. Now it does say, approximate any local minimum or maximum to the nearest tenth. So if we were going for our mins and max right now, our local mins and max, we're going to need that point and that point. But we already have a feature on our calculator that will help us do this. So let's do the first one with me. If we go for the one on the left, which is the local minimum, you would go to Calculate. And notice choice 3 is minimum and choice 4 is maximum, so make sure you're hitting the right one on the right value. We're going to the one on the left, which is the minimum, so we would choose choice 3. The first thing that comes up, it says left bound. You want to place your cursor, the little active bug, to the left of this point. So I'm going to place my little cursor bug right in here. So to the left of your lowest point. And so it said left bound, and it told me where I have it at, and I hit enter. Then it now says right bound, and I'm going to move my cursor over to the right side of the minimum point. Don't get it so close that it looks like it's right on it. Get it to the right side a little. And so that's the right side. So I basically, by my two locations, have chosen where it needs to look between for that local minimum. And now I'm going to choose enter again. And it'll say guess. I don't want to guess. I'm just going to hit enter. And it should spit out what the local minimum point is. And I said approximate to the nearest tenth. So on my calculator it says negative 1.09-ish. And so that would be a negative 1.1. And it says a y value of 1.98-ish. So when I round to the nearest tenth for my minimum, I would have been good. Now, I've revealed the maximum. Go ahead and do the same exact process. Calculate. You got to start over. Go to choice 4. Move your cursor to be places between that maximum point. And if I did that, my maximum point, I might want to place my cursor right about there and right about there. Do that, approximate, and see if you get your local maximum point. And again, round to the nearest tenth, I'm saying should be a 0.8 and an 8.3. Okay. All right. Now, noticing what you wrote there, and since you now know your local min and max to the nearest tenth, the next question says find the intervals over which the function is increasing and decreasing. We're always talking about left to right. So we would have to say it is definitely increasing from here to here, left to right. It's going up, 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 up. But from here to here, and I wanted to use a different color, from here to here, and from here to here, it's definitely decreasing. So you need to use these min-max values and write an interval, like an xy. So you can start thinking about what that would look like. And let's check. So it's definitely increasing from that negative 1.1-ish, which is what we got for our min x value, all the way up to the 0.8, which was the x value on the max. And then it is decreasing when it's less than that negative 1.1 and when it's greater than that negative, that positive 0.8. So we're using x values. We're using x values to determine this interval. Okay, so when we describe it, find the x value intervals. Because obviously you could do x and y, but it's just easier because you found them here. That's what you're going to go with when you write them here. And then just make sure you identify which one's increasing and which one's decreasing. Okay, looks good. Next one. Here was that end behavior that we're talking about. End behavior of a polynomial. Okay. Now let's just use that same equation we were just working at. Y equals negative 2x cubed, I'll just start it out like that from the last equation. Plus 5x squared plus 6, okay? And my little graph picture of it again was something here, then it went up, and then it came down. All right, just to give you an idea. So n behavior of a polynomial function. First, you need to know, is n even or odd? N is the degree of your polynomial, okay? And that would be your entire equation. So I'm looking at my equation here. It is in descending order. My highest degree is 3. So n is definitely odd. So right now for this graph, okay, for this graph I need to be looking at this row. N is odd. Then, is my a value greater than 0 or is my a value less than 0? My a value right now is a negative, so my a value is less than 0. I need to be looking at this. So it'll depend on your choices. So if I'm an even-powered graph, then do I have a positive first term or a negative first term? I'm an odd-powered graph, do I have a positive first term or a negative first term? So mine is a negative first term with an odd power, so it should be rising and falling. Now what does that mean? So take a look now at your graph. If I'm rising on the left, that means over here, the left side of my graph is still going up. It is rising. Where the right side of my graph, that's this portion, the end behavior is going down. It is falling. Okay, so that's all we're asking you to do. So look at the degree of the polynomial, odd or even, and is the first term's coefficient in standard form positive or negative? All right, so let's reset this page and let's try. Whoops. Let's try. Describe the end behavior of this one. So again, they're not even asking you to find the graph, but you can use the graph as a check in a second. So right now you look at this and say, okay, it's cubed. That's an odd degree, and it's definitely in descending order, so we're good. And then it's a positive, so it should be falling and rising. So now, if we would type in this equation, x to the third minus 2x squared minus 5x plus 3, and hit graph, we are looking for it falling on the left and rising on the right. And just to give you a little idea of what my grapher gave me, it's down here, then it rises and comes up here. It crosses a little past the origin, comes down here, and then comes back up. So to check it, you're saying, well, what do we need to do? It is falling on this end, and it is rising on this end. And that's all I'm looking at. I'm not looking at what goes on in between. I'm looking at the end behavior, the arrows. Okay, go ahead and try this one and jot down what you get, because that will be one we use as discussion in class to see if you get it or not. End behavior of a polynomial. Let's clean this off for you, and I'll put your equation back in view. So you're doing the r of x equation, asking yourself what's going to happen. Does it rise or fall based on the two pieces we need in the polynomial function? All right, after you have that, one more thing we need to talk about is how do we model with a polynomial function if they've given us real-life data? And this goes back to page 432 and the example that was in the book, number of high school graduates in the United States. And this happens to be part of example 3 data. And the directions say, find a quartic regression model for the number of high school graduates in the United States from 1960 to 1994, and again points A, B, C, D, and E represent 5 points that were chosen at random from that graduation list that they've given us. So we can make a scatter plot, see what it looks like, but if they just say use the quartic regression model, meaning we've already done linear regression, we've already done quadratic regression, and we've done one exponential regression. So if we were to take this one and do regression with it, we would follow those same rules we always have, and that has been to edit, make sure you're in L1 and L2, and our X data goes 10, 18, 30, 41, and 44. Make sure you've cleared out any other datas in your list, data pieces that is, and then it's 1679, 2606, 3089, 2276, and 2517. Again, making sure your X's match your Y's. You go back to Stat, you go to Calc, look at your choices. Since they told you this was a quartic polynomial, then you should be going to choice 7, quartic regression. Hit enter. It's saying, do you really want to do this? Hit enter again, and it spits out an equation for you that matches their generic setup, and their generic setup is y equals ax to the 4th plus bx to the 3rd plus cx squared plus dx plus e, and then they proceeded to give you a, b, c, d, and e. And if we said round to the nearest hundredth right now, double checking, these are the a values I got. Point, it would be rounded 0, 2. B, negative 1.94. C, 63.67. D, negative 723.74. And E, 4,296.3. Those would be the coefficients, and you would now have an equation. If they ask you, to calculate another value, you would, but it was done very similarly to how we've done the regressions in the past, and that's what we're expecting. So real-life data could be done, but the equation's going to be spit out by the calculator using your stat and regression possibilities. So if you have any questions there, bring them with you to class. We'll talk more about the graphs, the end behavior, take any questions you might have about any or all of that.